Okay, so we're going to start section 9.3. This is going to be several sessions long. So you have several assignments over 9.3. But first thing we're going to do is there's no solving quadratic equations, and the technique that we're going to use here initially is called the square root method. Okay, just a couple key concepts that we need to cover before we really get into that method, and these topics here are covering ideas for all quadratic equations. When we use this method, we're only going to be using it for a select few quadratic equations. Okay, so just remember a quadratic equation is an equation that can be written in the form ax squared plus bx plus c equals 0. Okay, so maybe we're looking at something like, x squared plus 5x plus 6 equals 0. Okay, so that's kind of the equation we're going to try to solve. So this is a nonlinear equation, more specifically classified as a quadratic equation. You guys know how to solve something like 5x plus 6. We have a structure, we have a set of principles and procedures and processes that allow us to solve this for x. Those procedures and principles and everything else that goes along with that are different for solving this type of equation. Okay, so solving linear equations is completely different than solving quadratic equations. However, the underlying concepts of the graphical approach is still the same for both types of equations, all types of equations. Okay, so that's kind of what we get down to right here. It says, remember that solutions to an equation are the x values for where the graph of the right-hand side of the equation crosses the graph of the left-hand side of the equation. I should say left hand. Okay, so let's give you an example of this real quick. Let's say I have the equation. Let's just write, because you've done this. We've done this together. I just want to jog our memory on it. Let's say the equation was, like 2x plus 3 equals x minus 5. Okay, we've gone through this enough that we could solve that algebraically and we get x equals -8. Okay, but if you remember, right, we demonstrated this and said, well, if we graph just the left-hand side, right, as y equals 2x plus 3. And then graph just the right-hand side, right, as y equals x minus 5. If we do that, these two things, if there is a solution, these two lines, graphs, curves, whatever you want to call them eventually, should intersect. And they intersect right there. The solution to this equation, then, is the x value in which they intersect. If I look at that point, A, the x value is -8, and that's exactly what we would have found if we would have solved this using our algebraic procedures or analytical approaches. Okay, so that's kind of what we're going to be doing here with quadratics. So now the left-hand side is just going to be a parabola, and the right-hand side is actually going to be a line, and we'll kind of explain that here. Okay, it says in each of the equations described by the above format, so this format here, we will be interested where the parabola y equals ax squared plus bx plus c, so that's what the left-hand side would mean. So if I had like x squared plus 5x plus 6, that would be a parabola. Okay, so we'd be interested in where that parabola crosses the right-hand side, and the right-hand side here would be 0, so where would it cross the line y equals 0? Okay, so those are the two things that we would graph. We would graph, obviously, the left-hand side as y equals that, graph the right-hand side as y equals that, okay? And when we do that, we'd be looking for then where those two things, or those two graphs intersect. Well, the left-hand side is going to be a parabola. So here's a situation where we have a parabola. This parabola is, you don't need to know this, but the equation for this parabola would be x squared plus 2. Okay, right here is the line y equals 0. So what we'd be asking here eventually, so if this is y equals x squared plus 2 and this is y equals 0, the question that they would have started us off with would have been, if I have x squared plus 2, when does that equal 0? Okay, well, when does this black parabola touch this red line? And the answer to that is never. So that's why we have what we call no real solutions. Okay, because there is no intersection between those two things. Okay, here, this is just the parabola here is y equals x squared, and the line here is still y equals 0. So we'd be looking at here as an equation that is actually x squared equals 0. So that's what they would start you off with. So the question, okay, well, when does that happen? Well, when does this black line touch, or black curve, parabola, touch the red line? And it happens one time right there at A. So that's a situation where we have one solution. Okay. Now this parabola eventually could be moved. We talked about this in the last section. We can move that parabola there so it touches at like 1. We can move it over here so it touches at -1. So there's a lot of different parabolas that could touch the line y equals 0 at one spot. We could even have them kind of looking that way. Okay. But there are situations where we have one solution. Here, this parabola, I think the equation here was y equals x squared minus 4. And this line was y equals 0. So they would start us off with the equation x squared minus 4 equals 0. So if they start us off with that, this is the graph that happens in the background, and we see that that parabola, x squared minus 4, intersects the line y equals 0 2 times at B and at C. So we would have two solutions. We have the x value of 2 for that one, and an x value of -2 for that one. So those are really the only 3 ways that a parabola and a line can intersect. So when we look at quadratic equations, you have 0, 1, or 2 possible solutions. Think about what we talked about with lines. Okay, something that was linear was ax to the first plus b equals 0. And our graphs that we could have had, just give you an example here of, most of your graphs are going to be like that purple line, and maybe that's a bad color to use. That purple line and that green line, they intersect one time. Okay, so we get one solution. Okay, but we also had a situation where we could have had that blue line and then that blue line, and they're parallel. Okay, and they don't intersect, so that was 0 solutions. Okay, and what I just want you guys to realize and recognize here, so if I had ax squared plus b equals 0, I had one solution or 0 solutions. Those are my only options. If we now have ax squared plus bx plus c equals 0, we just said we could have 0 solutions, we could have one solution, or we could have 2 solutions. Okay, and actually let me rewrite that just to see the pattern a little bit better. Let's go 2, 1, 0. We got 2 solutions, 1 solution, no solution. So now down the road, when we get to algebra 2, and you talk about like ax cubed plus bx squared plus cx plus d equals 0, we get to something like that. I just want you to understand from what we're talking about right now, you can decide or realize how many potential answers you could have. If we look at this, look at the most solutions that a line could have. It was equal to that number, or it was less than that number by an integer. So I take that number, subtract 1, and I get this one here. If I look at this one, okay, look at that number right there. It was the number of solutions are either equal to it or less than that by an integer. Okay, so I could have 2, subtract 1, I could have 1 solution, subtract 1 more, I could have 0 solutions. So my hopes are you can see the pattern. When I have something cubed, or to the 3rd power, that equation could have 3 solutions, 2 solutions, 1, or none. So that'll be a pattern that you guys investigate down the road. But right now, obviously, focusing on these x squared. So this is how many solutions we can have for the things that we do throughout this section and in the next couple sections. Okay, says the algebraic approaches should eventually tell us whether we have 0, 1, or 2 real solutions. And kind of investigate that a little bit here. Talk about the square root discussion here. What I want to talk about is square roots. So square roots are, let's say I have the square root of, let's just say 16. Okay, so this is a symbol for another number. Okay, generally that other number is irrational, so it doesn't terminate or repeat, so it's kind of like pi. In this case, this is a symbol for another number, and that other number is actually a rational number, which is 4. Okay, now there's a reason why I chose this, so I can describe what a square root is. Okay, this is a symbol for the number that I multiply by itself 2 times to get that number right there. Okay, so 16 is a special one of those. It's called a perfect square. You know other ones like maybe 9, so that's a symbol for another number. What number can I multiply by itself 2 times to get 9? So it's another symbol for 3. Okay, now here's kind of where this gets kind of confusing for some people. Like, let's say I have the square root of 5. Well, that's a symbol for another number. And that other number, let's see, I've got a program here. Let's see if it works. I was afraid of that. Let's try this real quick. I'll pause. Okay, so I've got this calculator up here. That's going to allow us to do this. So I've got square root of 5 here. Okay, and what I can do with this calculator is just ask it to change it from the symbol down to a decimal. Okay, so that is obviously, I think, 10 decimal places there or whatever. Okay, and actually I can guarantee that it's 10 by doing this. Okay, but look at that 7 right now. I'm not sure about that 7 because obviously you're not seeing any repeats here, like a repetitive pattern, like 2 3 2 3 2 3 or 2 3 6 2 3 6 2 3 6. I'm not seeing that in that description. So let's go to 11. Put out now one more term. Okay, I can go 15. And we start to see that there's really not a whole lot of pattern, but there are more decimal place values over here that my calculator just isn't showing. Like Desmos only show 10, TI-83s, TI-30s only show 10 decimal places. This thing can show a lot. So let's go 1,000. Okay, there's 1,000 decimal places, and there's no pattern there. Okay, meaning that no matter where I cut this off, no matter where I round this, I no longer have exactly the square root of 5. I have an estimation of the square root of 5. If I go out to, I think it's 100,000 decimal places, okay, you can kind of see how many that is, okay? So if I asked you to write the decimal value of radical 5 or square root of 5, you'd have to write that for 100,000 decimal places, yet that is still an estimation because this should go on forever, okay? And there's never a pattern and there's never an end to it. So I can't write that number down. So I need a symbol to explain that number, okay? Now here's the nice thing about this. I can say, let's just call this n, okay? So what this allows me to do is no matter where I hit n now, I'll just type n down here again, you're going to see that's going to reproduce that number. So just reproduce that number. So what I'm going to do real quick is just see what this does when I take n times n. And you see now, just because of rounding, I rounded this to 100,000 decimal places. So right there, it rounds us. But hopefully you guys agree that is pretty close to 5. Let's see if I can go eval f of n times n, comma, 10 decimal places. See what it does. Okay. Let's go 5 decimal places. Okay. So just because there's some calculations that go, but it is 5. If I go out to, let's go 500 decimal places. Okay, so the more decimal places I go out, the more accurate this can be. But I get now this number here, up here, that I cut and pasted, n times n multiplied by itself 2 times. You see that gives me back to 5. Okay. So that's kind of the idea behind square roots. Now, when we talk about square roots, there's a couple things to also work with and understand. When I ask the question, what number do I multiply together by itself 2 times to get 16? Obviously, 4 does that, but -4 also does, because we know a negative times a negative gives me a positive. So -4 times -4 still gives me 16. So when you square root a number, you actually get 2 answers. Okay? You get a positive version and a negative version, because a negative times itself is a positive. Okay? So that gets us into this next idea of something like this. What if the number under here is -16? Okay? If my answer, or my radical, is -16, the question is, well, what number do I multiply by itself 2 times to get -16? Well, think about this. If they're both 4, that would be a plus. So it can't be that. If they were both negative, that would be a plus. So they're not those. If that's positive and that's negative, that'd give me -16. +4 and -4 are not the same number. So they violate the rule or the definition of what a square root is. Okay? A number multiplied by itself. This number here is not itself right there. Okay? So that concept, that idea there, because I can't take a number and multiply it by itself 2 times and get a negative. It's impossible. Okay? So right now, and this will change when we get to algebra 2, you do not have an answer for this. Okay? This produces no solution right now. Okay? You'll find out that down the road there's a guy named Leonard Euler who came up with an invention, a mathematical invention that allows us to do this. But for now, when we get a square root of negative, we just say no solution. Okay? So that is going to, we'll spend a lot more time on it, and I wish our textbook did this, but I think chapter 10 talks about, it's a chapter just on radicals. I kind of think that maybe it would have been nice if that chapter would have come before this chapter, but it is what it is. All right, so I'll work with you on that. So just be I'm understanding of us not really understanding radicals at their fullest right now. All right, so we'll get to what we call a square root method, and this is the nuts and bolts of the material here. So this is the first and the easiest method for solving a quadratic equation, but you got to know when it works. It only works when we have equations of that form right there. Okay, you notice that there's no b times x term here. Okay, so all of our quadratics are of this form. Right here, basically, we're saying the b value is 0, so that term goes away, and all I'm left with is ax squared plus c equals 0. That is the only time that the square root method works. Okay, and these are the steps for solving this type of equation. The first thing you're going to do, you're going to take your equation, you're going to isolate the ax squared term. Remember what that means? That means get that all by itself on the left hand or right hand side. Okay, and you're going to do that by either adding or subtracting whatever c was from both sides. Okay, the next step will be to divide both sides by that a term. Okay, if it's there. Okay, here there is no a term in this example, or it's a 1, so I don't need to do that step. Okay, here the a term is 3, so I would divide everything by 3. But you'll do that. Okay, if your a is a fraction, okay, you can divide by that fraction, which is equivalent to multiplying by its reciprocal. So that's what I'm going to do. I'm going to multiply by the reciprocal. Okay. Step 3 then says solve for x by taking the square root of both sides. And then you got to remember this. It says taking the square root of a number produces two answers, one positive, one negative, as explained previously. Okay. And number 4, as always, we're going to check our answers using either a graphing technique or substitution with Desmos. Okay. So kind of get at this, and let's do some examples here and set you off on your 9-3 assignment. Okay, so first thing to do, isolate the ax squared term. So I'm going to isolate that. So to do that, remember, I have to look at what's over there with it. It's a -4. I need to get that to go to that side, so I'm going to add 4. Add 4 here. Because it's an equation, you need to do the same thing to both sides. So add 4 there. So there's a lot of our approaches that we've used with solving linear equations is still true here until really the last step. Okay, and we get to x squared now is equal to 4. Okay, and now I'm just going to look to see, is there a number out here other than 1? If there was, I would divide both sides by it. Okay, don't have to do that. Now what I need to do is I need to take square root. Okay, so I'm going to take the square root of x squared. Okay, so I'm asking the question, what do I multiply by itself 2 times to get x squared? Well, that answer is x. You multiply x by itself 2 times to get this x squared right here. Well, what I do the left-hand side, I have to do the right-hand side. So I take the square root of 4. So what number do I get when I take the square root of 4? What number do I multiply by itself 2 times to get 4? That answer is 2. Okay? Now here's the only thing that we got to pay attention to. When we take the square root of a number, okay, a known number, a visual number. So x squared is a number. I just don't know what it is. So I'm not going to do this over here with x squared. But 4, I know what that is. When I take that square root, there are really 2 answers. And I can write it that way, or you can write it x equals 2 and -2. You want to do it that way, separate with commas. I think, don't quote me on this, but I think Math Excel is going to ask you to separate your answers with commas. I don't think they have that that symbol with a plus or minus. All right, so let's go to the next one. Okay, so it's ax squared plus bx, it's ax squared plus c equals 0. That's the format. So we're going to move the c over to the other side. So I'm going to move that over. So I add 75 to both sides. Okay. So now this one's a little bit different than the last one because this number here is not a 1 anymore. So I need to make it a 1. So I need to divide both sides by 3. So you get x squared is equal to 25. Now what I'm going to do is I'm going to take square root of this side. I'll take square root of that side. Okay. The square root of x squared is just x. And the square root of 25, what number can I multiply 2 times to get 25? Well, it's 5, or it's -5. Those are my two answers. Okay. Let's check one of these. Let's check that one we just did. First thing we can do, we can just go, all right, let's graph y equals 0. Obviously, that's just the x-axis. Okay, and let's graph y equals 3x squared minus 75. And remember what we're trying to do. We're trying to see where does the blue parabola, having some zooming issues here. Where does the blue parabola intersect the x-axis, so line y equals 0? Well, I think you're seeing right there at -5 And right there at positive 5 is where they intersect. Okay. Another way of doing it is to obviously take the, so we had 3x squared minus 75. Now, I'm going to use, instead of x, I'm going to use a. And now I'm just going to say, well, let's let a equal 5. Does it give me the 0 that it told me I should get? Okay, when a is 5 or the x was 5, evaluate here, do I get 0? And I do. What about if it was negative 5? Do I get 0 again? Yes, I do. If I try any other number, let's try negative 4. You see that I don't get 0 here, so negative 4 would not be an answer to that solution, or answer to that question or equation. All right, so let's work on this one. Okay, again, okay, now in the first two we had 0 on the right hand side, but it doesn't matter, it could be any number over on the right hand side, like this one has a 2 over here. I still need to get that thing by itself. So add 14 to both sides. Excuse me, x squared is equal to 16. Okay, you're now going to take the square root of x squared, gives you x. Square root of 16, we've already talked about this. Two numbers that multiply together give me 16 are 4 or negative 4. Okay. So these next three here are similar but have some differing concepts. So this one here is just like the other ones, except for that is a fraction instead of a whole number. Okay. So talk about how we address that. Still going to try to, that's still my ax squared term, so I'm going to isolate that. So I'm going to add 10 to both sides. So 2/3 x squared is equal to 10. Okay. Now, per our steps up here, it says divide both sides by a, but if it's a fraction, multiply both sides by its reciprocal. If I divide both sides by 2/3, I get, divide a whole number by a fraction. The way you actually do that is you multiply by the reciprocal. So that's what I'm going to do instead. I'm just going to multiply this side by 3/2 because that's going to be 6 over 6, which is just 1. So it gives me 1x squared, and that's what I want. I want this coefficient out here to be 1. Over here, I need to multiply by 3 over 2. Now remember when I do that, so 10 times 3 is 30. 1 times 2 is 2. And now I get x squared, so 30 over 2 is 15. Okay, now here's where we get kind of messy. Okay, everything we've done so far, all the examples I've created here were intentional to where when we took the square root of this side, it gave us x. And when I took the square root of this side, it gave me a whole number, right? That number right there, 4, this one's 25, this one's 16. Those are all perfect squares. 15 is not a perfect square. There are not two whole numbers that you can multiply, or one whole number that you can multiply by itself twice to get 15. Okay? So what we're going to do is that when we do this and we recognize that that is not a perfect square, right now I just want you to write plus or minus radical 15. Leave it that way. Okay? Math Excel might ask you to round it to 1 decimal place, 2 decimal places, 3 decimal places. So if they do, just come to Desmos and type in square root 15, and you pull that number off. And here's the idea. Let's say that is, let me just say that number is n. So remember, I can go n times n. Does it get me back to 15? Okay. Even doing this, okay. Now it's going to give me something close to 15 probably. I don't know if it'll give me exactly 15 the way the calculator works. If I take that number times that number, that's pretty, now because of rounding error, okay, pretty close to 15. Because these were pretty close to the actual square root of 15. So that's kind of how you're going to approach those questions when this is not a perfect square in that last step. Okay. Okay, this next one. There's my ax squared. I need to move this plus 4 to that right-hand side. And that's going to give me negative 4. And now I'm going to take the square root here. Square root there. Okay. And now the question is, well, when I want to evaluate that. What number can I multiply by itself 2 times to get a negative? When we talked about it previously, there are no such numbers. You cannot do this. So when you get a negative under your radical, okay, this number under here is called the radicand. If you hear me say that word, if your radicand is negative, you're going to say no real solutions, which means that our parabola does not cross the x-axis. And if you think about what we talked about in 9.1 and 9.2, if this dotted parabola is x squared, then the solid one here is x squared plus 4. Remember, it just moves everything up 4 units. Well, does this solid parabola cross that line right there? The answer to that's no. And that's what that means. There are no crossings. There are no intersections. Jump into this question here. Same concept. Isolate that. So subtract 40 from both sides. So we get 2x squared. Negative 10 minus 40 is negative 50. Divide both sides by 2. I get x squared equals negative 25. Square root both sides. Get x equals plus or minus root negative 25. Again, if that number is negative, no real solutions. Okay, so that's the first type of equation that you're going to see in the assignment that I've posted. Those are it. That's the only type of quadratic equation that you're going to encounter. Email me any questions you might have. On the next session, we will talk about putting that b term back in. So we have x squared plus bx plus c, but we'll talk about some of the easier versions of that, and then we'll progressively get a little bit more difficult on the following session, so the 2 sessions from now.